So far in our inference portfolio, we have done 4 things, right? We have done 1, 2, 7, and 10 on our inference portfolio. Today we're going to add 3, okay? We're going to do confidence intervals. This is what we're going to do today. Confidence intervals for means, for one mean. And we're going to talk about what that means today. Okay, so after today, you should have close to half your portfolio done. We're going to make your portfolio due. I told you I'd give you a date, right? And that date is going to be mid-April when we get back, because I need to know when the end of the quarter is. So your portfolio will be due, it's a Friday, April 8th. You know it ahead of time. If you're absent, it's late. If it's not to me before April 8th, okay? You can email it to me if it has to get to that point, but it is due, and I will not accept it after April 8th. And I won't know how many are going to be on here until probably the week before, okay? But as of right now, these 5 are going to be due April 8th. Fair enough? Okay. I imagine there'll probably be at least 2, maybe 3 more to add. Okay, perfect. Today we are going to talk about more statistics, more inferential statistics, but we're going to talk about means. Do you remember how, where are your notes, baby? Get your notes out, please. We talked about at the very beginning of inference, we talked about how you had to make a decision in the problem about whether we were talking about proportions or whether we were talking about means. And you had to ask yourself that question. And for a long time, we've been dealing with the proportion side. We have formulas for the proportion. We know that the standard deviation is the square root of PQ over N. We know what the conditions are for proportions. And we've been dealing with that side. We're now going to switch to the other side and deal with means. Okay? Remind us what we already know about means. Let's start with the standard deviation. What do I do? It's not the square root of PQ over N anymore. What is it? So we had proportions, and we have means. The proportions, the standard deviation or standard error, whichever, was the square root of PQ over N. We had the conditions, where we had, the first 2 are always the same, but the different one was the NP is greater than 10 and NQ is greater than 10, right? What's different with those 2 things specifically when I'm talking about means? What's the formula for the standard deviation? Very good. Remember this? Remember that formula from before? Okay, so we're going to kind of switch gears a little bit, and this is what we're going to be looking at. Okay, you're going to be given a standard deviation. The conditions, we're no longer doing NP and NQ are greater than 10, but greater than 30. Our sample size is greater than 30. Okay, that's what we did before when we talked about means. Now, this problem is going, this condition right here is going to cause a problem for us. And we're going to talk about why in just a minute. And there's going to be a little bit of a glitch to that one, but we'll talk about it. Okay? So, what we're going to do with means is we're going to talk about the guy, this particular situation. Okay? Statisticians used to base all inference on the normal model. Okay? Everything was, we used normal CDF. Everything was normal. There was a problem with that. Okay, and this is actually a true story. This statistician named Gossett worked for Guinness Brewing Company. It's actually in your textbook. You can read about it in chapter 22. And he was a quality control engineer. Okay, he was rejecting too many batches that were actually really good. He was making too many type 1 errors. Why do you think that this sample size might prove as a problem at a brewery? Think about it. If I sampled more than 30, how is my decision-making process going to be? Probably not real good, wouldn't you say? Okay? So we had to come up with a different way to look at this. he was making some wrong decisions. Not necessarily because he was drunk, but because there were some other issues involved too. But he actually discovered that you can use smaller sample sizes and still make accurate decisions. And those but certain things had to happen. And we're going to talk about what those are. Okay? He actually developed by hand, and when you read this chapter, you'll see that. It took him over a year to develop this thing called the t-distribution. Okay? And it's very similar to normal. It just has kind of fatter tails, kind of like a little bit like Nicki Minaj. Okay? Got a little bit of a fatter backside. All right? T-distribution. Sometimes it's called student's T. Sometimes it's called Gossett's T. I just call it the t-distribution. Okay? The t-distribution is actually a whole bunch of distributions. It's a whole bunch of them based on sample size. Okay? As the sample size increases, it actually becomes more and more normal. So if you want to, I wanted to kind of give you a little picture, so you had a picture of what this looks like. The dotted line is the normal model. You know how the normal model gets really close to the x-axis? We call that asymptotic, right? It gets really close. Whereas the solid line is a t-distribution. We'll talk about what degree of freedom means in a second. Notice how its tails down here at the end are a little bit fatter, okay? They don't get as close. So it's kind of like the t-distribution's Nicki Minaj and like the normal distribution's like Taylor Swift, okay? She ain't got nothing back there, right? So we're going between the two, okay? And as our degree of freedom, and we'll talk about what that means in a minute, as that gets bigger, the more degree of freedom you have, the closer and closer Nicki becomes Taylor, all right? The closer that our t-distribution becomes more normal. Fair enough? All right. So I want to give you like a picture of what that looks like. What is degree of freedom? Okay, the degree of freedom, this is a formula you should write down. This is a definition. Because there are lots of distributions that use a degree of freedom. The t-distribution's one. If you've ever taken IB Bio, I think does t's, but do they do chi-squareds? No? Okay. I know that Math Studies does. IB Math Studies, but whatever. Chi-squared also has a degree of freedom as well. We'll talk about that in a couple of weeks. But the formula for degree of freedom is simply n minus 1. What's n? Sample size. And didn't I say that there's an infinite number of t-distributions? It just depends on the sample size. As the sample size gets bigger, our tails are becoming more and more closer to the x-axis, right? We're getting closer and closer to normal. So it depends on your degree of freedom. Okay? Look at this. Does that formula look familiar to you? There's a test statistic. It's no longer called a z-score. It's now called a t-score. Look at the formula. Isn't it just your statistic minus your mean divided by the standard deviation? That's what we've done all along. Your statistic, the mean that you capture, subtract the claim, the parameter, divided by the standard deviation, or standard error in this case. That's what we've always done for our test statistic. Okay? No big thing. What is the standard error, though? Well, think back to what we learned back at the central limit theorem. The central limit theorem says, why'd they use an S? Didn't you tell me before it was your sigma, your standard deviation, divided by the square root of n? Why is it an S? It's an S because we never know the population standard deviation. Okay? Why is it a standard error? Because we don't know that. We have to make it a standard error. Okay? So you're going to take a sample, you're going to collect some data, and from that data, you're going to find a mean, you're going to find a standard deviation, and be able to calculate some information. Okay? So not a whole lot different yet. We just have to know what this degree of freedom has something to do with it. On your calculator, you actually go ahead and on your calculator, go to where it says normal CDF. Where would you go when that happens? What do you notice right underneath normal? What does it say? It should say TCDF. Does it? It should. If you go to distributions, which is second vars. There we go. Do you see how it says TCDF as option 6? That we're going to use that just like we would use normal CDF. Okay? It's going to give us a probability. When do we use inverse norm again? When you're given the percentage and you want to find the z-score, right? Or the z-star maybe. Same thing. If that happens, notice there's an inverse t function on the calculator. So we can use it very similarly. Basically, when you're using means, you're going to use the t distribution. When you're using proportions, you're going to use the z's. Okay? That's the main difference. Okay, keep going. I've showed you that. So, what conditions are different? And this is where we need to pay close attention, because we're doing a sample for one mean sample, and the 10% condition's still there, the random sampling is still there. It's this last one. The sample size is greater than 30. We know that that will be safe to use, right? We already know that one. But what if our sample's not 30? What then? Can we do it? Yes. So if we have a sample that's smaller than 30, we still can use this distribution if the following things happen. If it's very small sample, then we have to be told the population's normal. Okay? Very small meaning smaller than 15. Okay? That doesn't happen very often. More often than not, what happens is that your sample size is somewhere between 15 and 30. If that happens, then we're looking at graphing your samples, making a histogram of them, deciding whether or not they're unimodal, symmetric, maybe doing a normal probability plot for them, looking for that straight line. We want to see, is our data relatively normal? Then we can use the t distributions. Okay? For large samples, greater than 30, you can use the t distribution even if your population's heavily skewed. Doesn't matter. Okay? How do we feel so far? Any questions so far? So, when you do your inference portfolio, and you're doing this for your confidence intervals and your tests, you've got to check your conditions for both, okay? So you need to be checking this condition for number 3 on your inference portfolio. I think the best thing to do is just jump in and do an example. And we're going to start with the confidence interval, okay? And that's all we're going to do today is confidence intervals. We'll do the actual test next class. And that, again, corresponds to number 3 in your portfolio. Yes, you will, because number 3 is a confidence interval. Okay? All right. Before we jump into the example, okay, the procedures are the same for means and proportions. The standardized score becomes a t instead of a z is the only difference. The distribution used changes to a t instead of the normal distribution. In the t distribution, you also need the degrees of freedom. You don't need to write that down. It's just kind of something that we know. Okay? Those are the differences, and those conditions are a little different. So this is what I want to look at, is this particular example. Okay? I don't live on Trip Hammer Road. Trip Hammer Road comes from the textbook, actually, but I live on a relatively main road in my neighborhood. It's like the main road that you come in when you drive on my neighborhood. And I got to tell you, these little teenage kids drive too fast on my road. And I get angry. So it's this not to blame the teenage kids, because there's an old lady who lives down the street, too, who doesn't know how to slow down either. So I can't really blame anybody. Just whatever. Anyway, this problem resonated with me, I guess is what I want to say. So let's read it. Let's make some decisions. I want to find a confidence interval, okay? 90% this time. We're going to be a little different. We're not going to do 95. We're going to do 90. What are some key pieces of information that you can pull from this problem? I've been given a standard deviation. I agree. Let's write what that is. And it's a sample standard deviation, so I'm going to label it with an S because it's based on my sample of 23 vehicles, and it is 4.25 miles per hour. Okay, give me another key piece of information. The sample size, and what's that? 23. Based on that sample size, I can right away go ahead and tell you what the degree of freedom is going to be. It's going to be 22. That's going to play an important part in what we're going to do in this problem. Okay? What else are we given in the problem? We know we're going to use 90%. Give me something else. We're definitely going to use the word random because we know that that's going to come into play when we check the condition. But what other number are we given? The mean. And what is the mean? 31. Okay. Let's remind ourselves what the formula for a confidence interval is. Remember on your formula sheet it says statistic, plus or minus. What is the statistic here? Is it a mean or is it a proportion? It's a mean this time. So the formula is this. I'm not using z's anymore because I'm talking about means. So normally we'd say z star here, right? We're going to use t star instead. And then what is it multiplied by? If you look at the formula on your formula sheet, it says standard deviation of the statistic. Well, what would that be in this case? The formula for means is your sample standard deviation divided by the square root of the sample size. So it's the same thing, it just has different letters attached to it, that's all. Before we jump into it, I think we should check the conditions. Okay, we're going to put some numbers in here, but let's make sure we can do it. Let's check the conditions first. So what are the conditions? There are 3 of them. What are they? Give me one. Katie alluded to it earlier. Say it. Go ahead and remind us, Katie. It's a random sample. I agree. What else? Well, independent from what? And I can't say independent, so what am I going to use instead? The 10%. So give me a number that I'm going to use. 23 is less than 10% of all cars that travel down that road, right? I agree. The last condition's the unusual one, right? My sample is not large enough. I don't know. It's not greater than 30. So what do I have to do instead? I have to, it's that middle one, right? The sample size is between 15 and 30. It's that middle of the road kind of thing. So what do I have to check? Let's go back and just remind ourselves. If our sample size is in this blue category here, the data should be unimodal and symmetric. Am I told that here in the problem? No. But we need to check. So believe it or not, I have the data. Let me find it. Here it is. I'm going to pause for a minute. I want us to graph it. Let's see if we can do this. This is back in September. Do you remember how to graph and find a histogram of this data? Let's see if we remember. Okay, so I'm going to pause the recording. I want you to put it in. The recording. I am going to enter, you can do this as 2 columns. You can put the speed in list 1 and the frequency in list 2. But because the frequencies aren't that big, I'm just going to write them down that many times. Is that okay with you? So in other words, I'm going to put 29 in 4 times. I don't have to do that, but it's just going to save me some time from having to put another column in. Is that okay with you? If the frequencies were really big, I would use that, but they're not. And we have 30. So let me go to the other side, and we'll plug it in. Okay. Do you remember how to go about finding a histogram here? Where do I go? If I go to y equals, make sure there's nothing there. My plot's not turned on. I got to do that. Remember how to turn my plot on? Stat plot. We're going to turn it on. Which plot am I looking at for a histogram? I'm looking to see if it's unimodal and symmetric. The type is that one right there, right? Histogram. Okay. And then if I want to have it show up, zoom stat. Remember this from a while ago? So zoom stat, I believe, is option 9. And we have not too bad. I mean, it's not perfect. Remember, the calculator is kind of funky sometimes. It doesn't give it exactly right, but it's definitely not skewed, super skewed. Would you agree with that? So to satisfy this part of the conditions, you better sketch that and say it's relatively unimodal and symmetric. We can go on. The other option, you don't have to graph both. You can either graph the histogram, or the other thing that will satisfy this condition would be the normal probability plot, which is the last one. What am I looking for that to look like? What do I expect it to look like in order for it to be relatively normal? A straight line. Okay? So let's look and see if it does. I'll go to zoom stat again. It's pretty straight. You could graph either, but you need a little sketch in order to answer that question. Okay? That condition. So let me just go back for a second. We're doing our conditions here. And what am I going to do here? To me, this one's a little easier to draw. So I'm just going to draw that one. And I'm just going to say relatively normal. If you wanted to sketch the histogram, that's okay. Okay? You might want to say because our sample equals 23, we had to graph that. It was in that 15 to 30 range, right? So I had to check the graph. So are my conditions met? Yes. We having an issue with the calculator? All right, so can we do the confidence interval? Yeah, we checked our conditions, we're good. So let's go ahead and fill in the numbers that we know. The x bar is 31. We'll come back to the t star. The standard deviation is 4.25 divided by the square root of 23. I just got to find that t star. How did I find the z star when I did it before? I did inverse norm, so I'm not going to do that. I'd have to use inverse t. Okay? But didn't before we just memorize them, a lot of you? Just 95%, you just memorize it to be 1.96 and whatever. On your test, though, there was a weird one. Remember, 97%, you had to find it? So how would I do that here? This was a 90% confidence interval. Okay? So we know that. But if I'm going to draw it, the 90 goes in the middle. What goes on either tail? 0.05. I only care about one of them, really. I'm looking for T star. So how do I plug that in? Well, normally it'd be inverse norm, but we're going to do inverse T. Go ahead and plug inverse T into your calculator. What does it ask you for? It asks you for a couple of things. If you do inverse T, there we go. Inverse T, the area is 0.95, wouldn't you agree? Because it's the middle plus one of the tails. It's also asking for the degree of freedom. Why? Because it wants to know which one to use. Okay, what's our degree of freedom? 22. So we're going to paste that sucker, and we get 1.717. That's going to be the T star that we're going to use, 1.717. Okay? So I'm going to pause the recording. I want you to tell me what the confidence interval is. All right, so 29.48, 32.52, that's fine. Interpret it. What does it mean? It means numbers. It means something more than numbers. What does it mean? Okay, stop right there. That is amazing. That is exciting. That is perfect. That's always how you start your confidence interval explanation. We are percent confident that. In this case, we're 90% confident that. If you don't start your interpretation that way, I'm going to choke, okay? You got to start it that way. So yes, we're 90% confident that what? Say it louder. No? Context is miles per hour. Remember, we're checking speeding here. That the true mean speed on Trip Hammer Road is between 29.48 and 32.52 miles per hour. Okay, that's what that's really saying. Let's actually write that down so we know. Okay? We are 90% confident that the true, we're not trying to capture zero this time, are we? Because we're not talking about the difference between two things. We're back to one sample again, right? So we're not looking at trying to capture zero. We're trying to capture the true mean speed. Okay, that's fine. What if the posted speed limit in this neighborhood was 30 miles an hour? Let me finish my question. If the posted speed limit is 30 miles an hour, how could that change my interpretation? Can we say that cars are speeding? No. Cars are not speeding. Because even though the mean was 31, which implies speeding, 30 is inside that interval, right? We captured 30, so we can't say they're speeding. What if the posted speed limit was 25 miles an hour? Is 25 captured in there? No, which means they're speeding, okay? So that's what you want to look for in this case. Perfect. I really think I want to stop there, okay? We talked about new distributions. We introduced degree of freedom. We have new formulas. We have to figure out how to find T star, which is not, it's going to be different every time, right? We can't just memorize T star anymore because it just depends on the sample size. It's different every time. So you're really going to have to be able to use this to figure it out, okay? This part here in your confidence intervals is what's going to be new and different, okay? You've got to do that on your homework. So what is your homework? Let's talk about that. Your homework first is going to be to do any extra credit that you haven't done before. Remember, you have two options for that. You have that online assignment, and you have the last problem from the notes from Wednesday. Which was the 9th. You also need to be working on your inference portfolio. I keep saying that because I don't want you to wait until the last minute. Remember when it's due. What did we say? April 8th. And then you're going to have to read chapter 22. And you're going to do some textbook problems. The problems are page 598, problems 10, 12, 17, 18, and 20. Okay? So you have about 15 minutes now. You are not to pack up. You are not to get ready to go. I would like for you to either to do one of these things, whether you're working on the extra credit, whether you're grabbing a textbook from the cart and working on the textbook problems, or your inference portfolio. You have some choices. Okay?